Today, our group will present experiment number 6 in hydraulics, which is titled Flow Rate and Energy Loss Measurement using Weirs. For this experiment, we specially use the Crump weir, which is type of triangular weir with a flat crest. It's widely used in hydraulics and engineering for flow measurement and monitoring due to its accuracy and stability. So, in our group, this experiment number 6, which is titled Flow Rate and Energy Loss Measurement using Weirs, we have main objectives, which is we have two main objectives. Number 1, to determine the flow rate or the discharge of water as it passes over the Crump weir or the triangular type of weir. And we have number 2, to observe the changes in water flow and energy as it interacts with the weir, especially in any loss in head or changes in depth. So instead of using floating objects like ping pong balls, we focus on visually observing the behavior of water and gathering the measurement data for analysis.
So for this experiment, we use the hydraulic bench or flume in our lab. It's a transparent open channel designed to let us observe the water flow in controlled environment. The Crump weir was securely installed at a fixed point in the flume. This weir type has a sloped triangular face and horizontal flat crest, which helps in producing a more stable flow profile. So we adjusted the flow using the flume's valve controls to maintain steady water discharge. The water was dialed for better visibility, which helped us clearly observe the depth before and after the weir. So our group carefully observed the water surface profile as it approached weir, passed over it, and flowed downstream. Guys, so this is teaching flume. Tuturuan namin kayo kung paano siya gamitin. So, maraming types of weir. Merong rectangular, triangular, and Crump weir. Yung sa amin is Crump weir. So, tuturuan namin kayo muna ngayon kung paano gagamitin to. Teaching flume. So, para ma-open siya, kailangan siyang i-taas lang dito. Tapos, magkakaroon na ng water. Para ma-adjust nyo naman yung discharge actual, merong measurement here. Naka L over H siya, so liter per hour. Dito nyo lang i-adjust kung mas mataas yung discharge or mas mababa. Yan lang po.
So before performing the main experiment with the Crump weir, we first conducted observations using a rectangular weir. This allowed us to compare how different weir shapes influence water flow and discharge. The rectangular weir has a straight horizontal crest, while the Crump weir features sloped sides and a flat crest, performing a triangular shape. So using the flume setup, naobserbahan namin how water behaved as it flowed over the rectangular weir. We also measured the upstream water depth, also known as the head, and used this to estimate the flow rate based on the weir's specific formula. The flow over the rectangular weir appeared sharp and linear, with a sudden drop after the crest. After that, we removed the rectangular weir and replaced it with the Crump weir. We adjusted the flow to a similar level and again recorded the head upstream of the weir. Unlike the rectangular weir, the Crump weir caused the water to flow more gradually over the sloped face, producing a smoother and more stable water profile. So visually, napansin din namin that the water surface rose more steadily when approaching the Crump weir compared to the rectangular one. This change in flow pattern highlighted how the geometry of the weir influences the distribution of water before and after the crest. The Crump weir allowed for a wider and gentler flow transition, so in terms of discharge, both weirs gave measurable results, but the Crump weir was observed to be more stable and lower flow rates. Its shape makes it better suited for a broader range of discharges, particularly in natural or irregular flow conditions. The rectangular weir, while simpler in design, tends to produce more turbulence at the crest. So overall, comparing the rectangular weir to the Crump weir helped us understand the importance of weir design in regulating and measuring flow. Even though both serve the same purpose, the Crump weir offered a smoother and more controlled flow, which is why it is often preferred in field applications where accuracy and flow stability are important.
So after completing our initial measurements without any obstruction, we installed the Crump weir in the flume. The Crump weir is distinct because of its triangular sloping sides and flat crest, which allows for stable flow measurements over range of discharges. Its design helps in producing a well-defined flow pattern, making it ideal for experiments that require an accurate and repeatable observations. Once the Crump weir was in place, we began by adjusting the water flow to maintain a consistent discharge, and then we carefully observed the change in water behavior, especially the way the flow gradually increased in height as it approached the upstream face of the weir. This increase in height, known as the head, was one of the critical parameters we had to measure to estimate the discharge over the weir. We located the measurement point a short distance upstream from the weir where the flow was undisturbed and subcritical. Using a scale attached to the side of the flume, we recorded the depth of water above the weir crest, and then this head measurement is essential because the flow rate was a Crump weir depends directly on the head value. The higher the head, the greater the discharge, so precise measurement was the key. As the water flowed over the weir, we noticed a smooth and uniform water sheet forming along the crest. This smooth flow confirmed that the flow was within the acceptable range for the weir and not overflowing or creating turbulence, which could have affected accuracy. Downstream, we observed a drop in the water surface level, which is typical and indicates energy loss, and as the flow transition from a higher to a lower elevation. By comparing the upstream and the downstream depths, we could clearly see how the Crump weir influenced the flow. The difference in height visually demonstrated how potential energy was converted to kinetic energy, and some of it was lost due to friction and turbulence. While we did not compute the exact energy loss in this experiment, the visual cue gave us an understanding of how structures like weirs impact flow behavior in open channels. Overall, this part of the experiment highlighted the practical function of the Crump weir in both regulating and measuring flow. It allowed us to apply theoretical concepts like head and discharges relationships. In a hands-on setting, we observe how the flow reached to the weir in real time helped us understand not only the mathematics behind discharge formulas but also the physical principles of energy transformation and control in hydraulic systems.
Once we completed our observations with the Crump weir installed, we were able to compare the results with the flow we observed earlier with the rectangular weir. One of the most noticeable differences was the increase in water depth upstream of the Crump weir. This is expected as the weir temporarily holds back water to measure the rate of flow based on the height above the crest. Using the measured head or vertical distance from the crest to the water surface, we were able to estimate the discharge of the flowing water. The relationship between the head and discharge is already defined for the Crump weir, so it became easier to relate the depth measurements to flow rate. Throughout the experiment, we focused mainly on visual observations, watching how water moved as it approached, passed over, and continued beyond the Crump weir. The flow remained smooth and stable, which is a good indicator that the setup was functioning properly and the measurements were accurate. The Crump weir is a simple yet effective tool that can be used in practical situations like irrigation canals, drainage systems, and rivers where water flow needs to be measured or managed. Its triangular shape and flat crest make it ideal for measuring a wide range of discharges. This experiment showed us the importance of careful observation and correct measurement techniques in hydraulic engineering. Even without using high-tech equipment, we were able to gather useful data by understanding the basic principles of open channel flow. In summary, our experiment with the Crump weir gave us a deeper understanding of how flow rate is influenced by structural controls in a channel. It reinforced the value of hands-on learning and showed how hydraulic structures like weirs play a key role in water resource management.